Hello, my name is Alexis Pena, and I'm the team lead for the Sidewalk Slope Monitoring System project this year. Together with Jan, Hua, Abigail, Anna, Cristina, Pabasara, Beatriz, and Aoqian, we've worked with the City of Los Angeles Bureau of Engineering to pick up where the last team left off. Our senior design advisor is Professor Jungsoo Lim, and our liaisons are Ted Allen and ALISA Blade. However, we had the pleasure of working with many other people on their team. We're really excited to tell you more about our accomplishments this year, but first a brief introduction on the project. Our project first started in 2019, where the previous senior design team was then tasked with creating an affordable multitasking rover, which can gather and analyze sidewalk data and report its findings back to an LA City field agent. Similar to how a Mars rover would roll on Mars and collect information, our rover would do the same, but with a much smaller budget. Our goal on the project was to remove the manual aspect of having someone go out in the field, measure, and calculate whether a sidewalk has met ADA compliance. If you take into consideration that concrete sidewalks are prone to break and that Los Angeles has over 11,000 miles of sidewalk, you can start to visualize why our project was first conceptualized. Measuring a single sidewalk might sound simple, but keeping 11,000 miles of sidewalk ADA compliant is a more difficult task. And so with a working rover prototype provided by the last team, our team was able to pick up right where they left off, and we're working on manipulating the rover data and creating software and infrastructure needed to package everything into a new and improved rover provided by the Bureau. Our team was assigned 4 important tasks to tackle throughout the school year. The first was to create a web application which would map the data collected by the rover. 2 was to create a rover user interface which would allow the field agent to control the rover. 3 was to implement an image processing in order to get enhanced image and extract useful information. And last was to create a backend database to collect, store, and manipulate data. The LEO rover, like as I mentioned, was provided by the Bureau of Engineering and has helped us expand our project tremendously. The rover is an outdoor robotics development kit with a custom running ROS operating system, which runs off a Raspberry Pi and has custom firmware. It's extremely robust and has allowed us to expand beyond our needs. On the left here, you can see version 1 of our rover, nicknamed Rebecca, which was pieced together by the last senior design team. And on the right, you can see the LEO rover, which our team had the pleasure of building from the ground up. And now Hall will go over the web application side of things.
Thank you. One of the tasks of our project is to create a website so that we have a place to display all of our data and images. Later on, as we develop our website, we add additional pages to explain why we are working on this project and why it's important, which we have discussed in the introduction. Next slide. When we first started this project, we created a simple framework of a single page to display our data. The page would display information vital to our project, such as the image's name, slope of the sidewalk, and the coordinates to see where the sidewalk is located at. The image lets us see the real damage of the sidewalk. For the image, we want to be able to iterate through our database using previous, next, and auto button, as well as to pan, zoom in, and out of the image. We also plan to implement a search bar to look through all of our pictures by the image's names or coordinates the image was taken from. However, as you might have noticed, the framework does not look much like a website page. Next slide. Therefore, we updated the framework to include a navigation bar, additional pages, and a footer to make it look more authentic. As you can see, additional pages we have include a home page, a database page, about page, and a page to redirect to a website called Navigate LA, which displays the layout of LA City. The home and about page gives us additional information for our project, such as why we are doing the project and how it would help the city. For the fall semester, we have finished creating the UI, and for spring semester, we have implemented the features of the website. Next slide. One of the features we have implemented is the zoom in and pan functions, which is similar to the functions used on Amazon, in which when you hover over a part of the image, such as the blue square you see on the right, a section of the image appears on the left, as you can see. This lets the user see a zoomed in image as they move the mouse around the original image. As the user moves the mouse on the image, the zoomed in image on the left will move corresponding to it. In the next slides, Anna will introduce another function we have worked on. Next slide.
One of the issues that we encountered was what image should be shown next to the user. We couldn't rely on image IDs because it wasn't an accurate representation of location. For example, if the rover stopped collecting images for the day and on the next day started on a different part of the city, the IDs would not match up as shown on the image to the right. Next slide. And another issue was how users should switch between images. We had originally planned for a previous next button, but in the cases of large complicated intersections like the one shown in the image, users can't exactly go left or right. They would have to have at least a few different image options to choose from. Next slide. So instead, our approach was to use Google Maps and Embed Maps. These can be added to a website and can contain points of interest markers. For example, with the image shown on the left, we have some for Skid Row, downtown LA. And on the right, we can see that the embed maps actually allow users to zoom in and out, or even switch to satellite mode. It's more interactive than the buttons we had originally planned. Next slide. We also explored what we could do with the markers. We can remove typical point of interest markers and instead use them to mark where rover images are captured. So with the second image, where if the user was in the circle, the X markers would be removed, but the orange ones would know where the user would be if they were in the circle. Next slide, please. And with our web application, all of the images related data is shown in the console. Users can focus on one particular image or instance of the sidewalk data. But currently, BOE uses the mapping application Navigate LA, and it helps to visualize data from reports produced by the city, county, and other associated agencies. Ideally, the sidewalk data would be added as a layer on Navigate LA so that BOE can visualize their data in one location. Next slide. And to determine how the sidewalk data should be visualized, we needed to consider the city's prioritization and scoring system. They've developed a system that assigns a numerical score to sidewalk segments to determine which sidewalks require immediate attention. Next slide. And using AutoCAD, we can automate the creation of DWG files that can then be hosted and visualized on Navigate LA. The two criteria that we focused on were cross slope and running slope, and their severity indices are identified by their color. So with the image on the right, we've shown an example of how we can visualize part of the slope data. And for this semester, or for the fall semester, I should say, we focused primarily on determining how we can visualize the data and what programming languages would work best. So this was placed on hold for the spring semester per the LIAISON's request. And future efforts for the web application side of the project would be to test the website and Google Maps and Embed Maps with large amounts of data from the database and making it accessible to city employees as we currently host it locally. And efforts for the expansion of the AutoCAD and Python automation would be to send up the servers to host the layers and Navigate LA. And now we'll be moving on to image processing in the next slide.
Hello, I'm going to talk about image processing. So first, we need to find canny edge detection. That is very useful technique in image processing. It could extract useful information from different vision objects and reduce the amount of data to process. But before that, we need to blur an image. It makes the color transition from one side of an edge to another smoothly. The effect is to average out rapid changes in pixel intensity. The blur an image removes outliers pixels that may be noise in the image. It will help us to analyze where is disjointed in the image and then find broken sidewalk. And then the broken area can be marked. Next slide, please. There are some steps that show how we process an image. The right part of slide, image A is get canny edge detection from source image. You can see that is messy and we cannot get much useful information because there are some stones on the road and that will be hard to extract data. So we need to blur the image like B. It's just like a filter to remove noise. After that, C shows we can get a clear edge. It separates the sidewalk into different parts, and then we can find the corner of the edge and figure out where it's broken. Then mark that area as result like left side result shows. Next.
The goal in task for image processing is to find the vertical and horizontal displacement of the sidewalk with a 2D image. We are unable to utilize machine learning or AI at the moment because testing and training requires a lot of images and feature extraction functionality. Therefore, currently our task is to count the pixels of an image to scale the image to real measurements. This is important because this might help us satisfy our goal to measure the vertical displacement of the sidewalk from an image. This is the distance created when land is shifted vertically. Then we have horizontal displacement of the sidewalk, that is the damage created on the sidewalk, like the image on the right. It is a challenge to find the horizontal displacement from a 2D image because the camera won't give us an overhead view. With the 2D image, it is a challenge to distinguish both these displacements, but with image processing and future AI implementations, we're hoping to at least distinguish if the sidewalk has a displacement or not. Next slide. In order for us to measure the sidewalk, we first need to extract the pixel dimensions of one point of the image. To do so, I created a function to extract the points that are selected. The image on the left shows us an example of lines that are drawn on the image by hand. If you look to the image on the right, you can see the points are created by clicking on the edges of the sidewalk in red, and the blue lines are for precision, assuming the camera is straight. You can see that the point 1 is located 468 by 686, and the point 2 is located 1783 by 686. This is how the pixel dimensions are extracted. Next, Jan will talk more about image processing algorithms used, measuring the displacement, and our future plans.
Thank you, Pabasara. The GrabCut algorithm is an algorithm in OpenCV that is used on images for foreground extraction. As you can see from these images, we begin with the original image and end with just the sidewalk. All the noise has been removed. To do that, we need some user input. We need the help of editing a copy of the original image to draw some strokes, which can be seen in the lower left. Black denotes background and white denotes foreground. Then we run the algorithm to get this binary masked image located at the top right. Combine it with the original image, we end with only the sidewalk. After image segmentation, next slide please. We will measure the X and Y displacement in centimeters. Before, we were using the GoPro Fusion camera to take images, but it could only take circular fisheye images, and it was difficult finding the distance between the camera and per pixel from just a 2D space. Fortunately, we have the Intel RealSense depth camera. It can gather color and depth data. The left is the colored image, and the other is the depth image. They are both PNG, but PNG does not keep depth data, so we need to record the frames and save as a bag file or save depth image as RAW. After that, we need to align both the colored and depth frames to match the pixels to each other, which the Intel RealSense SDK kindly provided. Then, given the 2-point camera intrinsics and depth data, we called some functions that can obtain the 3D coordinates relative to the camera in meters. Finally, we can use Euclidean distance to calculate the displacement between the two 3D coordinates in meters, then convert it to centimeters, which is simply multiplying by 100. Next slide, please. Future planning. As there are more than 11,000 miles of sidewalk that needs to be overseen, manually masking each individual image To get rid of the background noise and then select 2 points to find the displacement would still take a long time. Therefore, having an AI do all this would be more ideal and efficient. Knowing those displacements can help contribute to let the AI automatically label the condition for each sidewalk. This will allow us to know the priority of which sidewalk needs immediate fixing. However, we would need a numerous amount of sidewalk data to sufficiently train the AI. Maybe we can at least make the masking part automatic to reduce the workload until then. Next, Cristina will speak about the Rover UI.
Thank you, Jen. So our task was to redesign the Rover user interface. We will be overviewing how the user interface looks now, how it previously looked, the data display, and the Rover move mode controls, as well as the complete UI. Now on the next slide. The Rover UI has now been organized to display all functionality in a simple yet effective design as displayed in the picture. The main display now features new buttons that will make navigating the Rover movement and all data collection easier for the field crew. All the buttons that have been rearranged and organized are the Start button that initializes the GPS and simultaneously starts the LEO Rover camera as well. The Start button also initializes the data collection and motor functionality. The Stop button stops the data collection. The Turn off will shut down the Rover. The Data Display button displays all data that have been collected. The Export Data feature allows field workers to export all data collected so they can view and analyze the data, since this is saved as a CSV file on the micro SD card located on the LEO Rover. Lastly, the Rover Mode button organizes and displays the Rover movement functions that will allow clear access so that the field workers can control the movement of the Rover. On the next slide, we will see that we have integrated the 2 new buttons that have consolidated the Rover movement and organized the view for all data that have been collected. The photo on the left is the Rover user interface now, where we have combined all Rover movement functionalities together. The Rover mode has 5 controls that will allow the field workers to move the Rover in order to collect data, such as move forward, backward, left, right, stop the Rover, and control the speed as well. The photo on the right is the data display, which displays all the data that the field workers have collected in one session in a separate window. This table displays the coordinate, time, date, GPS location, data orientation, and pin ID, as well as image ID data. Now, Beatriz will go over the previous version of the Rover UI and our complete user interface.
Now, the previous UI was designed by last year's students and was used to control the rover that was built by them, which was called Rebecca, and has a completely different system than our rover. This year, we have a new rover called the Rover that our team has now assembled, and we have also begun to test our UI. On the new design, as Cristina previously presented, we have made the improvements as far as providing structure and organization to make data collection and rover movement easier for the field team. We have developed 2 new sections that have consolidated all rover movement and data to be controlled and displayed. So in the next slide, we're going to talk about the completed UI. Our final version of the UI is displayed on the left side, where we have completed the UI that the rover will use in order to move and collect data. The rover mode control buttons have been redesigned. Data display mode has an export mode CSV file so that office users can access it easily and begin analysis. The data display has also been designed to save space and displaying to the table, as well as closing this data table. Furthermore, the on the right displays the UI that the rover originally has come with. In comparison with our UI, it does not include the data display or the capability to export any data collected. Now Abigail will go on to talk about the backend database.
The Backend Database group will discuss hardware and data, database, and Azure Blob Storage, the relational schema, automation, as well as expansion. Next slide. Prior to any SQL code being written, we first had to consider what we were working with. The Rover has an open-faced platform full of different hardware, which all has its own specific data that needed collecting. Things such as the level, LiDAR, depth camera, GoPro 360, and the GPS module. Once we had pinpointed the data, which was crucial for the project's success, we analyzed the type of data, the quantity, and its relevance before moving on to the next step, which was software. Next slide, please. For anyone unfamiliar with the backend database side of things, there are a few different options which provide the necessary tools needed to properly store things on the cloud or on a physical server. These include popular name brands such as Amazon AWS, Google Cloud Computing Services, and Microsoft Azure, to name a few. Each of them have their own perks, but more importantly, their own subset of available tools and costs. After further discussion with our liaisons, we made the choice to pursue Microsoft Azure for our backend database because it's not only the best tool for the job in terms of services, but also implements quite easily with BOE's current environment. Next slide. We found that Azure Blob Storage was the best fit for the database requirements, being a cost-effective method for scalable data storage and no limits for data. These factors are necessary for our project, specifically for saving the thousands of images coming from the rover, such as the front, rear, and rendered images. As seen on the right diagram, an account recording the rover's data will hold an image container which records a link to the blob storage holding all image files. Alex will now continue discussing the database functionality.
And so the backend was a very crucial part in our project. It not only took into consideration the rover and its hardware and how it communicated and saved data, it also served as the backbone for our web user interface, allowing them to pull and read data and display it, and also allowing the AI team to process their images and save it as well for testing. The SQL database ties everything together and helps us keep the necessary data for our project success. And with so many moving parts with the rover and its hardware and then the backend database, it was important to keep automation in mind when designing everything. This is just one of our flowcharts that demonstrates how data is automated from the Leo rover into our blob storage containers and then into our SQL database tables. So if you were to start here on the left with the Leo rover, you can go down and see some of the hardware that we have in place. So if we were to take the GoPro, we would grab a GoPro image from it and then run a Python script, which would then extract necessary information from its metadata. That data would come in the form of an Excel sheet, which would then be thrown into the blob storage, which would automate a trigger, which would then pull the Excel sheet, grab the information within the Excel, and populate SQL tables with that set data. Everything done automatically with just a few physical steps. And on a more technical sense, this is a relational schema from within the database after the Excel sheets have been populated. And it's all designed not only to connect with our blob storage, but also to connect with existing tables provided by the Bureau of Engineering. And again, if you would start on the right here near the Azure Blob Storage folder, you can see how it then connects to the data factory, which does a lot of the automation and orchestration, allowing us to create and populate our tables with our existing Excel sheets, and then tying these tables together with other tables which already existed within the BOE's environment. And so with existing storage solutions, working UIs, and image processing, the project is in a good state for future implementation, such as severity levels, data manipulation, and even artificial intelligence. This concludes the Sidewalk monitoring project presentation. Thank you.